everybody. I am Ming Jin. I graduated from Berkeley and recently became a Hokie in the ECE department. My research is on optimization, control, and learning with a focus on developing trustworthy algorithms for safety-critical systems like the power grid, and it resonates with cyber-physical security and resiliency and human-centric technology. The ultimate goal is to substantially improve the efficiency, reliability, security, and resiliency of urban infrastructures by developing the full potential of data and algorithms. Now, my research is motivated by the fact that existing techniques are found to be data hungry, difficult to explain, and extremely brittle under attacks, which make them far away from being trusted to do the critical work. To address these issues, I mainly work on optimization as it intersects with control and machine learning. Now, in many cases, the design of a data-driven decision-making algorithm can be converted to an optimization problem, but there are some universal challenges. The first challenge is nonlinearity that arises from the underlying physical system. As a result of that, the optimization landscape is quite complicated. So, of course, we want to find the global optimum, but if we start from a wrong point by following a descent path, we might arrive at a local solution. And in general, there are no efficient algorithms to solve it. For example, in power grid, the annual cost of doing approximation is way over $1 billion. That's the first challenge. Now, the optimization that we solve is built on data from the real world, but we no longer have fine-grained control over the quality. If part of the data are corrupted and solve this optimization problem again, even if we have the best solver to find the global solution, it will be meaningless because the objective is biased. So even formulating a meaningful optimization would be a challenge. And of course, we want to solve problems fast and in real time. But as urban infrastructures become increasingly large scale, scalability becomes an issue. And in many cases, we have humans in the loop or on the loop. So the design of an algorithm that can interact with people and even augment their behaviors is a challenge. So along these directions, we have been developing techniques in optimization, control, and learning inspired by problems in power and energy systems. For example, we came up with the first vulnerability map of the entire US grid to assess the security of data-driven decision-making systems in the power grid against cyber attacks. It has implications for stakeholders like utility and regulators to design strategies for grid hardening. Also, we are one of the first to came up with theoretical guarantees of reinforcement learning to be safe and stable in nonlinear systems, which have implications for practitioners who are interested in applying reinforcement learning to solve real-world challenges. To scale up data analytics, one major bottleneck has been the lack of hand-labeled data. So to alleviate this issue, we have developed the technique of weekly supervised learning to leverage domain knowledge, and we demonstrated that it can be used to tap into the vast data generated by millions of smart meters to understand household activity patterns. Last but not least, we have been working on theories to understand people's intent based on their behaviors and use it to design incentives that softly nudge people in the right direction, for example, to save energy. Now, over the years, we have found that it is interdisciplinary research that is motivating people, uncovering new challenges, and pushing the technology at a fundamental level. And I've been fortunate to collaborate with researchers in multiple disciplines and domains. As data and algorithms become increasingly important in our daily lives, we aspire to solve problems with interdisciplinary nature at a scale to realize the dream of smart cities. Thank you.